Yeah. So it is a pleasure to introduce James Martin from Oxford. He's an old friend of our community in Brazil and Argentina. And he is talking about geodesics in last passage percolations and second-class particles in TASEP.
Thank you very much indeed, Pablo. Thank you. It's really nice to talk to you guys, and it's far too long since I came to either Brazil or Argentina, and so hopefully when the world is back to normal again, we can start doing those things. But it's lovely to be here. Thank you very much for the invitation. So yes, this is going to be joint work with Allan Sly and Lingfu Zhang, who are both from Princeton. Lingfu is a student of Allan. Oh, Pablo, how long do I have roughly? What time should I aim for?
Have 50 minutes, so it's until 13:55. So.
Okay, it's 55. Okay, great. So this hopefully, there'll be a paper hopefully on the archive in a week or two. It's kind of in final draft stage. So it's about particular problems in last passage percolation, which we attack using ideas from interactive particle systems, so the TASEP in particular. So this is the fundamental model we're looking at, which is the directed last passage percolation model in 2 dimensions. So we've got the square lattice Z2, and at each site of the lattice, we've got a weight, and these weights are i.i.d, and they're all exponential 1. So if we've got any 2 points, u and v, where u is below and to the left of v, we define a passage time from u to v, and this passage time is the maximum over all directed paths from u to v. So you look at paths which go from u to v using steps that go up and to the right, like this one that you see here, and that path passes through a whole lot of sites of Z2, and the weight of the path, so these weights are called WZ, and the weight of a path gamma is just a sum of all the weights of the sites along the path. Okay, and that is called the passage time from u to v. And the geodesic, this should say g of u, u v. Okay, the geodesic from u to v is the gamma that maximizes that weight. Okay, so please do interrupt at any moment if anything's not at all clear. So these passage times satisfy some nice recurrences, which are going to be relevant later on. So for example, if we want to know the maximum passage time of a path from u to v, well, that's just going to be the weight at v plus the maximum of 2 things, either the passage time to the point to the left of v or the passage time to the point below v. Okay, any path from u to v has to pass either through this point to the left of v or the point below v. So we take the maximum of these 2 things here, and we add on the new weight, which is the weight at v, and then we've got the passage time from u to v. So this is by now extremely well-studied model, and there's a lot of so this is an exactly solvable model. There's tremendous amount known. Let me just write down the maybe one of the very first things that was shown about this by Herman Rost back at the beginning of the 80s, and that's a law of large numbers. So if we look at, let's say, a path from the origin at distance n in the direction xy. So x and y are any 2 positive numbers. So you look at the path from the origin to point xn, yn, you've got a law of large numbers, and the weight of that path grows like n times this function of x and y, which is square root of x plus square root of y all squared. So in particular, you could think of a case where x and y are 1. So you just look at the passage time from 0, 0 to nn, and that behaves like 4n. So that's nice linear behavior, and that follows, well, the fact that there is a law of large numbers follows quite nicely from some kind of subadditive ergodic theorem. But by now, an awful lot more is known. So for example, the fluctuations around that law of large numbers are known in great detail. So they are of the order of n to the third. So the passage time grows like, let's say passage time from 0 to 4n behaves like 4n plus something random on the order of n to the third. And another thing we know, for example, is about the fluctuations of the path itself. So you look at this geodesic, it behaves roughly like a straight line between, say, 0 and nn. But the fluctuations around that straight line are on the order of n to the 2/3. So there's this 1/3, 2/3 scaling, which is very characteristic of systems in the KPZ universality class, which this is. Okay, so that's the basic model. Is that everyone happy with that? Because those are the definitions I've been using throughout. Okay, so my thing is not scrolling very nicely. I don't know where that is. There we go. We're going to be looking at a particular question, which is about the local behavior around a geodesic. So let's take, for example, a geodesic from, say, the origin up to the point nn. And let n be very big, so we've got a very long path. We can just zoom in on a particular point in the path. So this point here may be a point V like this, and say, what do we see locally around V? So in particular, we could ask, what weights do we see locally? What are the weights like around V? And what does the path look like? What's that little bit of the path around V looking like? So in particular, you could ask, for example, about the sequence of weights along the geodesic near V. So this stuff is called we call the environment. So for example, we could use this notation here, W of V in curly brackets. That's just notation for the field of weights around the point V. Okay, that should be Z squared there, sorry about that. So all the weights we see sort of centered around V. And we could write this kind of pair here. So this is the weights around V, and this is the geodesic from, let's say we've got a geodesic from A to V. We can look at that geodesic, but shifted by V again. So we just want to see what it looks like around V. And we could do this for any V that's on the geodesic. So what should these weights look like? So you can imagine that as you go along a geodesic, you expect to see weights that are non-typical, because you're choosing that path because it goes through heavy weights. You're trying to maximize the weight of this path. So the weights you see along the geodesic should be typically larger than just an arbitrary weight. And in fact, so we know that for example, the weight of a path from 0 to nn, so that's got 2n steps, and it tends to have weight around 4n. So a typical weight along that path should have mean 2 in some sense. Okay, whereas a typical weight in the plane has got mean 1. Okay, so already you can see that the weights are heavier than usual along the path. So it's a bit more notation. We're just going to, so let's write capital gamma n for the geodesic between 0, 0 and nn. And I'm going to write mu n for the empirical measure averaged along that geodesic. Okay, so we're going to take this thing here, which is the sort of environment seen from a point V. We're going to take delta measure at that environment and average that over the whole path. So that gives us a random measure on the space of environments. And we can think of that space as, well, we're going to see a field of weights. So we see r to the z squared, and we're going to see a geodesic, and I can just think of that as a set of points that the geodesic goes through. So this is some measure in r to the z squared, which tells me the weights, and 0, 1 to the z squared, that just tells me for every point, does the geodesic go through that point or not? And then, so our theorem is going to be about the convergence of the distribution on these environments. And we can either think of it, so the first part of the theorem says that the empirical measure converges to some limit, some deterministic limit. And the second part of the theorem says that the distribution of the environment around some given weight converges. Okay, so we take some, so for example, we could take the weight that's halfway along the path. We could take the nth weight on the path, which is just the halfway point, and we could look at the environment around that point. That will be alpha equals 1, but we could take any other alpha, and we're looking at the environment around the this notation here means the point, which is the alpha nth point on the geodesic. And so the law of that also converges to this same law as n goes to infinity. Okay, so is that making sense, what I'm trying to state and prove there? So we're just zooming in on a point on the path and asking whether the environment seen around there converges. And we can think of this either in this average sense, taking an average along the whole path, or we can think of it as just the law of any given point on the path. So I should mention there's recent work by Eric Bates, who's in Madison, which attacks a similar problem. So he's looking at first passage percolation, or also directed first passage percolation. And in some sense, his results are well, massively broader than our results, because he's looking at a very general set of weight distributions. In some sense, he can show that, so this can be in 2 dimensions or in higher dimensions, so any d greater than or equal to 2, that if you have some some edge distribution, then you can take a sort of arbitrarily small perturbation of that edge distribution and get a model for which you can show convergence of the empirical distribution of weights. So we're in a very much more specific situation, but we're going to correspondingly, we've got all this extra kind of exactly solvable firepower to throw at things. We're going to be able to show stronger things, and particularly we're going to be able to identify very nicely what this limit actually is. So we're going to give an explicit construction of our limiting distribution nu of what the environment looks like, and we can calculate various properties of it. So here are just some examples of things we can calculate. We can get the distribution of a typical weight on the geodesic. So if you take the empirical distribution of all the weights on the geodesic from 0 to nn, you'll get a distribution which converges to the thing with this density function here. So this is some mixture of gamma distributions. And you can check, if you like, that it's got mean 2, which is what it needs to have. Or we could ask something about the shape of the path. So this path is a sequence of up and right steps. And of course, if it's going from 0, 0 to nn, it's got to have half steps up and half the steps to the right. But you could ask, how often does it change direction? So how many of the steps repeat so go up, up again, or right, right again, and how many of them turn at 90 degrees to the previous step? And we can show, for example, that the proportion of corners, the proportion of these turning points converges to 3/8. So that's just 2 examples of the kind of things you can calculate. So here are the kind of things that are going to go into the construction and into the proof. The key thing is going to be a link between geodesics in last passage percolation, so in particular semi-infinite geodesics, which I'm going to talk about in a minute, and the path of a second-class particle in the TASEP. So I'll define the TASEP, and I'll tell you what second-class particles are for people who haven't seen those things as well. And in particular, we're going to be able to relate this distribution nu of the environment around a point in the geodesic with the stationary distribution of a TASEP as seen from a second-class particle. So those are 2 of the elements. And then to kind of back that up, we need a lot of quite intensive work on the geometry of geodesics in last passage percolation. So in particular, properties of coalescence of geodesics starting from nearby points and that kind of thing. Estimates on the fluctuations, estimates on what the tree of geodesics looks like. Okay, so need to introduce a few more technical things. So this is the idea of semi-infinite geodesics for the last passage percolation problem and Boozerman functions. So what is a semi-infinite geodesic? So let me tell you first in just sort of heuristically, we can look at the geodesic from, let me maybe just draw this briefly here. Oops, My scrolling is going crazy today for some reason. I've now gone almost to the end of the talk. Okay. Right, here's a blank page. So let's take a point V in the plane. And actually we're going to consider, let's consider geodesics between V and points below it on the left. So we can consider the point, the geodesic between U and V, or we can consider the geodesic between V and some other U1 that comes down there. And maybe that geodesic looks, maybe it starts off sort of the same, and then at some point it comes off and goes towards U1 like that. Or I can think of the geodesic between V and U2 for some point down there. So maybe that one follows the red path for a while, and then it's going to come off and do something like that. And the idea is that as I let U2 get further and further away in the kind of direction down and to the left, I'm going to make sure that it always goes, let's say it always goes in this direction, -1, -1. Then this path from V to that point a long, long way away down and to the left is going to converge to some infinite path. Okay, so maybe the infinite path it converges to, maybe we've got some path again that follows here, and then this infinite path carries on like that. So this geodesic converges in that sense. So that's the thing we're aiming to construct. Let me show you a more technical way of constructing it. So via this thing called a Boozerman function. So we're going to have a function G from the square lattice to R, and define it in the following way. So G of V, we're going to think of paths from -n to V. So again, we're going to take n to infinity, and this is going to be a long, long way away in the southwest direction. And we're going to compare the path from that point to V with the path from that point to the origin, and take that difference there. So G of the origin is 0. And so, for example, if I if I take a point that's so let's take the origin here, I can compare this path here with a path from here, let's say. So that's my point V, and at some points those paths will join up, and the difference between the passage time from this point to 0 and the passage time from this point to V is going to be the difference between these two paths here. Okay, and if these points are very close together, then very likely these paths will join up very quickly. They could even join up in one step. Okay, so if I take the point just to the right of the origin, it may be that the difference is just one weight. It could be that the point goes through the origin here. But the point is, we've got, this function is again going to satisfy these local recurrences. If I take the value of G at V, well, that path down to -n for any n, and so that path down to infinity as well, is just going to, well, it's going to have the weight at V, and then that path is going to have to go through either V, either the point to the left of V or the point to the point below V. Okay, so again, this was just a very similar type of recurrence to the one we saw on the first slide for finite geodesics. And the point is now we've got this field of values G of V, which obey these recurrences locally. And now we can construct these infinite geodesics starting from any point. I've got a value of G of B, and I'm going to look at this recurrence here, and I'm going to say, well, which of these 2 points here has the larger value of G? Okay, so I go from V to either the point below or the point to the left, whichever one has the larger value of V. And then so I repeat again. So now from maybe the one on the left, I go either down or to the left. I'm always trying to maximize this value of G. And in this way, I get what's called an infinite path, and every step goes down and left. And this gives what's called a semi-infinite geodesic. So this gives us a path which is going to have direction -1, -1. And every finite segment of this path, So if I take this W, there's this half infinite path, I take any 2 points on the path, the segment of that semi-infinite geodesic between those 2 points is the geodesic for last passage percolation between those 2 endpoints. Okay, and it turns out that this geodesic is actually, with up to almost surely, is specified by those 2 properties. Okay, so there's a unique path in direction -1, -1, which has that finite geodesic property. So there's a couple of very nice kind of expository papers recently by Timo Seppäläinen, some lecture notes from 2018, and a recent paper, I think, in Annals of IHP, where he has very nice sort of survey, very nice construction of how all these Boozman functions and semi-infinite geodesics and related ideas work. And here's a very nice fact that we've built a down left path by sort of maximizing G at every step. So we use these recursive, from every point we went to the way which maximized the value of G. We can do something similar and build an up right path by going to whichever of our neighbor above or our neighbor to the right minimizes the value of G. So this gives us another infinite path. And this is going to have the direction 1, 1. So it's going to go in the exactly opposite direction. And it's going to have a finite geodesic property, just like the path that went down to the left, but not anymore for these weights W of Z, but instead for some dual weights, which I've called W hat of Z. So we've got some field W hat of Z, which obeys a very closely related property. I wonder if I've written this right. Yeah, okay. So we've got a set of recurrences for this path going in the other direction. And so these are the G along this path is going up and to the right. The values of G are increasing. And these weights W hat of Z are again the differences as you move along this path. And a very nice fact, which I think I learned first from Pablo and Leandro Pimentel, is that these dual weights W hat of Z are also i.i.d. exponential 1. We'll see in a minute the link between last passage percolation and the TASEP, and one way to think about these dual weights in terms of a time reversal of the TASEP. So you have a link between last passage percolation and the TASEP, and the jump times in the TASEP are governed by these exponential 1 random variables, W. And if you reverse time, you get a reverse time version of the TASEP, which is a process which is then governed by these dual weights, W hat. So I think maybe this sort of exact form of the theorem there was first in paper that Pablo and Leandro and I wrote about competition interfaces for last passage percolation. But there were some other sort of already at that stage, very similar ideas being used, for example, by Martin Bollasch and Eric Katar and Timo Seppäläinen in their work on fluctuations of last passage percolation geodesics and that kind of thing. Okay, so the form of the theorem I wrote before was about finite geodesics, but actually we can also ask about what happens along these semi-infinite geodesics, and that turns out to be easier to prove directly. So that's really what we start off by proving, is a related result along a semi-infinite geodesic. So take the semi-infinite geodesic, this gamma infinity starting at any point V, and we can define the environment seen around the rth point of this geodesic. Okay, so again, we could look, let's say, at the first n points of this geodesic, the semi-infinite geodesic, and average over those, we get this empirical distribution here. And this empirical distribution converges, or there's now a very obvious coupling of these things, and we get convergence almost surely now to our limiting distribution nu. But we could also just pick, let's say, the rth point of our semi-infinite geodesic and look at the environment around that point. And so the law of the environment around the rth point, again, converges to our limit nu as r tends to infinity. So actually, the result for finite geodesics is going to be, I'm not going to show you the details, but the result about finite geodesics in the end is going to come from saying that a long finite geodesic can be kind of covered with high probability by bits of semi-infinite geodesics going in different directions, so that if we have this kind of convergence for the empirical distribution along semi-infinite geodesics, then we can also derive it for long finite geodesics as well. Okay, any questions or things to clarify at this point? Okay. So the proof is going to, I'm not going to show you by any means really anything that constitutes a proof, but I can show you the ideas that are going into the proof, and in particular the ideas that go into the construction of this limit nu, and they revolve around a TASEP. So there's a lot of you will already know the idea of the link between last passage percolation, exponential last passage percolation, and the TASEP, but let me show you it again for people who haven't seen it. So the TASEP is a particle system on Z, and each site of Z has either a hole or a particle. So we're going to, if we call the holes zeros and the particles 1, then we've got state space, which is 0, 1 to the Z. And the dynamics are that each particle which has a hole to its right jumps to the right at rate 1. Okay, so you can think of that as whenever you see a hole followed by a particle, then at rate 1, those two things swap round, and you see after the jump, you see a particle followed by a hole. So the places in this picture where we could do jumps are there's a possible jump there, there's a possible jump there, there's a possible jump there, and so on. And you can think of this extended in infinitely in both directions. And there's a very nice set of translation invariant stationary distributions. So for any density rho between 0 and 1, if you take Bernoulli product measure, under which each site is occupied with probability rho and empty, so each site is a particle with probability rho and a hole with probability 1 minus rho, then that gives you a stationary distribution for the TASEP, and all the translation invariant stationary distributions of the TASEP are mixtures of those Bernoulli product measures. So let me show you the link between the TASEP and last passage percolation. So the simplest setting maybe to see this link is just doing last passage percolation in the quadrant. And that corresponds to starting off the TASEP from a very specific initial condition. So we're going to start the TASEP off from an initial condition where, let's say, from 0 leftwards, we have only particles, and from 1 rightwards, we have only holes. Okay, so we've got this, this initial condition here, and we're going to couple the evolution of the TASEP to the evolution of a growth model. Yeah, so we start off with an empty quadrant, and we're going to add cells 1 by 1 in the quadrant. So the first jump that can happen in the TASEP, the only thing that can happen from the initial condition is this jump here between, so I've labeled here the particles from 0 upwards going to the left. Okay, so going leftwards, we have particle 0, particle 1, particle 2, particle 3, and so on. And similarly, the holes are labeled from by non-negative integers from left to right. So the first jump of this process, which is going to happen after an exponential time, is going to be that particle 0 and hole 0 are going to swap around. So after that's happened, let me maybe just try and do a little thing in real time here. So after that happens, our process is going, our configuration is going to look like that. We're going to have particle 0 here and hole 0 here, and I'm going to add this cell here. And at this point, there are two things that can happen in the TASEP. The next thing that happens is either of these two jumps, either particle 0 swaps with hole 1 or particle 1 swaps with hole 0. So maybe let's say particle 0 does another jump. So that would be this jump here. And that would go to this configuration here now, and we would add that. And maybe I'm not going to keep changing the configuration, but maybe the next thing is that particle 1 jumps to its right, and we add that thing there. So what does it mean that a cell here, what does it mean that cell 1, 0 has been filled in? It means that particle 1 has swapped with hole k. Okay, so you can imagine n indexing the particles and k indexing the holes, and you fill in the site like that when particle n swaps with hole k. So here below it, we've got a little picture of what might have happened after a few steps. And there's a nice way to think about what's going on here. So we started off with, at this point, we've got a kind of interface around the edge of our set, our occupied set, which looks like that. We started off with an interface. Before anything was filled in at all, our interface went just down and then to the right. And you can think of every step down as a particle. So starting up here at sort of minus infinity, we're reading off the configuration in this direction. So we see particle, 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 and then hole, 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 hole in that direction. And at this point, we see a whole load of particles. And then finally, we see a hole, and then two more particles, and then a hole, and then a particle, and then a hole, and then a particle, and then a lot of holes. Okay, so your interface sort of links up to your configuration like that. Okay, so T and K we could call the time that particle n and hole k exchange. So that's the time that we add the cell nk in the picture. And that turns out to be the weight of the geodesic in last partial percolation from 0, 0 to nk. And that's because we have exactly, we can couple these things so that they've got the same, they obey the same recurrences. So let's let WNK, you wait, that's going to be the time it takes for particle n and hole k to exchange once they've got next to each other. So you wait until particle n and k are next to each other. The time that happens is actually this here. In order for particle n to be next to hole k, we need particle n to have got past hole k minus 1, and we also need particle n minus 1 to have got past hole k. Those are the two things we need for particle n and hole k to be next to each other, and then we wait an exponential amount of time for them to swap round, and that gives us the time that particle n and hole k exchange. Okay, so that's the simplest coupling between TASEP and last partial percolation. But we could also do a version for a stationary TASEP, so a TASEP with product measure. And that we can relate back to this Boseman function. So we're going to now consider a growth model on all of z squared. We're going to add cell z1, z2 at time this Boseman function g of the point z1, z2. And in the TASEP, that g of z1, z2 is going to represent the time that particle z1 and hole z2 exchange spaces. So now we've got actually particles labeled by all of z. So we've got particles with positive labels and particles with negative labels, and the same with the holes. And if you remember so g of 0 was just defined to be 0. So at time 0, that's precisely the time when particles 0 and hole 0 have switched places. So this cell here, this green cell in the middle here, 0 is precisely the time, that's the cell 0, 0, and 0 is precisely the time that that cell gets occupied. And so 0, if we see here particle 0 and hole 0, which I've drawn with in the green box, that is, so at time 0, we see that those two have just exchanged places with each other. Okay. And at time 0, so we've got some, again, I could draw a sort of this red interface here. And if I follow along this interface, it tells me I've got particle, hole, 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 particle, hole, particle, particle, like so. And so that matches up with this configuration on the right. And I happen to know, okay, so I just know that, let's say at site 0 and site 1, I'm going to have this hole particle corresponding to hole 0 and particle 0 there. But everywhere else, I actually have Bernoulli product measure with density a half. So I've got this kind of hole and particle in the middle, and then everywhere else, I've got probability a half to have a particle and probability a half to have a hole. And then if I let time move from 0 onwards, so I now let time increase. So on the right, we're going to see these particles and these holes exchanging places with each other. And then in this picture, we're going to see new cells being added one by one to the picture like that as the particles move around. Okay, so our growth model is going to evolve and our TASEP is going to evolve, and we've coupled those things together. Get rid of those new things. Okay, so the next idea that I need to introduce is the TASEP with second-class particles. So a second-class particle in the TASEP is going to be something that's halfway between a particle and a hole. So in this picture here, it's illustrated by these things with stars in them. So these are second-class particles, and these ones are particles, and the small dots are holes again. And a second-class particle can switch places with a hole to its right, and it can jump onto where a hole is, but it can be jumped onto by a particle. Okay, so it can switch places with a hole to its right, but it can also switch places with a particle to its left. So for example, we can see here we've got a possible jump where the particle to the left and the second-class particle to the right exchange places, but we don't have a jump here. We can't let the second-class particle can't exchange places with a particle to its right. Here we've just got a particle in a hole, that's normal. Okay, and so here we've got a second-class particle that can exchange places with a hole to the right. And we're going to look in particular at systems with a single second-class particle in them, so just one, an isolated second-class particle. And there's a very beautiful idea which comes from, again, from Pablo and Leandro, which is that we can represent this isolated second-class particle in the TASEP by going back to a system which has only holes and particles, and we replace this second-class particle by two sites, one of which contains a hole on the left and one of which contains a particle on the right. Okay, so you can see hopefully what I've done in that diagram here. So to represent this configuration here, we've replaced the second-class particle by a box which covers two sites and has got a hole and then a particle. And you can see, okay, so this second-class particle can exchange places with the hole on its right. So that's, in that case, that just corresponds to this particle inside the box exchanging places with a hole to its right like that. And when that happens, so we end up in this configuration here, and we've moved the whole box to the right. Okay. But the reverse thing could happen. It could be that we exchange places, this second-class particle wants to exchange places with a particle to its left. Okay, and that corresponds to that particle exchanging places with the hole inside the box. And at that point, we shift the hole left. We shift the box left. Okay, so this box is going to either jump right or left. And if we follow this rule, the box always covers a hole and a particle. Okay, so if you want to know which way the box is going to jump next, you have to ask yourself, well, which of these two events happens first? Does it happen first that this particle here exchanges with this hole here, or whatever that maybe there is? Maybe that hole isn't even there yet. Maybe we have to wait for that hole to appear, or is it the case that the first thing that happens to something in this box is that the hole here exchanges with a particle to its left? Okay, one of those two things must happen first. And if it's the thing at the right, then the box moves right. And if it's the thing to the left, then the box moves left. And that just corresponds to this particle, the second class particle, moving left or right here. Okay, is that construction making sense? Pablo is nodding, but I know that Pablo also already understands this construction. So the key idea now is that we can again label our holes by Z increasing from left to right, and we're going to label our particles by Z increasing from right to left. So we have something that looks like what we've got at the bottom here. So I've got the particles labeled in red and the holes labeled in blue like that. So this green box, this whole particle box, which represents a second class particle, is going to cover hole K and particle N for some K and N. And what this tells us is that, okay, so particle N has got to the right of hole K. So the event that happens at time GNK has already happened. But the event that happens at time GNK plus 1 has not yet happened. And the event that happens at time GN plus 1K has not yet happened, because otherwise these things would not be next to each other anymore. But one of those things is going to happen first. Either, so if the event that happens at time GN plus 1K, that means that this jump here is going to happen next. And if instead it's the other one that's smaller, if that time is smaller than, sorry, there should be an N plus 1 here, then that would tell us that this thing is happening next. So you're going to look at which of these things happen first, and that's going to tell you which way to move the box. So either the box, let's say the box was covering hole 2 and particle 6, like we've got here, either it goes to its right and it moves to cover hole 3 and particle 6, or it moves to its left and it moves to cover hole 2 and particle 7. Those are the two possibilities. And this is just the same rule as we had for constructing this geodesic that went up and right. Okay, we said, well, you look at the point above you. So you're at 0.26, let's say. You look at 0.27 and you look at 0.36, and you say, which of those 2 points has the earlier value of G? And you go to that, your new point on your path is whichever one was earlier. So the jumps made by this box, made by this second class particle thing, are exactly the same as the jumps made by the semi-infinite geodesic G hat, which goes up and to the right. Okay, so I can kind of try and show you what happens on this picture here. We've got our box. Let's say we start our box over this hole 0 and particle 0, which we know we start with next to each other at time 0. And we want to know which way this thing is going to jump. So we can watch the evolution of our particle set, of our growth model, and we're going to add these cells one by one. And the first question I want to answer is, which of these two places, these two dots here, which of those two gets filled in first? And when I know which of those two gets filled in first, that's where I'm going to take my geodesic, and that's going to correspond to my movement of my particle. So let's say, for example, it could be that this one to the right gets filled in first. So that means that that's the new location of my geodesic, and that actually corresponds to, I think, I may have this the wrong way around, but I think that corresponds to this jump here happening. But then, okay, so then a few things have to happen. Now I'm going to ask myself whether, whoops, so I can get rid of that one there, and I'm going to ask myself whether this or this get filled in next. Now, quite a lot of things have to happen before either of those can happen, but I again watch my thing evolving. Maybe these boxes get added, and then eventually I get to a stage where I can add that one there. And so the thing has gone up at that point. And then maybe, okay, then I'm interested in which of these two gets added next, and so on. So I follow, in the end, this kind of green path is going to continue something like that. And each step of that green path is going to correspond to a jump of this second class particle. And actually, the sequence of times between the jumps of the second class particle corresponds exactly to these dual weights along this geodesic. So if I am interested in what weights along a geodesic look like, it's really just the same as what the times between jumps of the second class particle look like. So let's write that down as a theorem. So we consider a TASEP started with just one second class particle at the origin, and everywhere else we put Bernoulli product measure. So we put a particle with probability half, and we put a hole with probability half independently everywhere. So this particle is going to jump, the second class particle is going to jump left and right, and the times between its jumps are exactly, that sequence has exactly the same distribution as a sequence of weights along a semi-infinite geodesic. And if you look at whether that particle jumps left or right, that's telling you whether this path of the geodesic is going right or up at each step. So what this tells us is that basically if we could understand the world seen from this second class particle, then we would understand the environment around a geodesic. So I'm not going to tell you that in great detail because I'm going to run out of time soon. But this question of what the world looks like from a second class particle is has been studied for a long time, and it started off in early to mid 90s. So in particular, what we would like to understand is a process where, let's say we've got a single second class particle. We start off in maybe this configuration I've got here. This second class particle is going to jump around, but when the second class particle jumps around, we're going to stay with it. Okay, so you can imagine yourself sitting on top of the second class particle, and you want to see what the world looks like from where you are. So if the second class particle jumps right, you see everything else shifting left. And if the second class particle jumps left, you see everything shifting right. So you see things going past you, but you think that you're just staying at the origin the whole time. So you see a configuration of particles and holes to your left and your right. And that is the process of a TASEP seen from a second class particle. And we can ask what a stationary distribution of that process is. So we're going to start off in product measure with just each site occupied with probability half with a particle or a hole. But it turns out that product measure is not a stationary distribution for this process. And one way to think about that is that the second class particle can kind of get stuck behind holes. So sorry, stuck behind particles. So if there's a lot of particles in front of it, it can't get past them. And it can also get stuck in front of holes. Okay, it can't exchange with particles to its right. It can't exchange with holes to its left. So it can get stuck in those positions. And so actually we see slightly, there's a stationary measure for this TASEP seen from a second class particle, which was constructed by Pablo with Fontes and Hayakawa, which has the property that it pretty much has density a half of particles. So if you go to infinity in either direction, you see density a half of particles. But the density of particles is very slightly greater than a half on your right, in a way that kind of decays to a half as you go to infinity. And it's very slightly less than a half on your left, in a way that goes up to a half as you go to minus infinity. And these kind of measures, so they were also studied sort of in the physics literature. Derrida, Janovsky, Lebowitz, and Speer was one of the first places they were looked at in that context. And you can, if I had more time, I would really like to show you how these come up when you're studying shocks for the TASEP, for example. And there are various different, so Pablo with Fontes and Hayakawa had a nice combinatorial construction of this measure, and there were various sort of variations of this that happened later on at Angel, and then in work I had with Pablo later as well, we had sort of different combinatorial constructions of this measure, but it could be constructed in a very nice way as a function of two symmetric nearest neighbor random walks. This makes calculations with it very, very nice and easy. And it's actually, one nice thing about it, we can couple it with Bernoulli product measure in such a way, so near as we get far away from the origin, we see something that looks very much like Bernoulli product measure, and we can couple it so that the probability of discrepancy at site X is decaying like, that should be X to the minus a half. Okay, so we're starting, if you remember the picture that we had back here, we're starting, our geodesic is starting from the origin. At that point, what we're seeing to our left and our right is product measure. So what we'd like to see is what happens to our second class particle if we start in, I'm sorry about this scrolling. For some reason, my iPad is going crazy today. Okay, it's taking me right back to the beginning. Let me go maybe via a different route, and this is the slide that we want. Okay, so this is the kind of result we need. We're going to start the TASEP basin from a second class particle from Bernoulli product measure. So let mu be this stationary distribution, and let phi t be the distribution at time t. So we get, this sort of seemed obvious that this must be the case, but I think this doesn't seem to have been known before. And it turns out to be somewhat, at least our proof of this is quite involved. It doesn't seem to be a very easy thing to show, is that phi t converges to mu as t goes to infinity. So if you start in product measure and you let time evolve, then you are converging to the stationary distribution as seen from a second class particle. And along the way, so going with this, we show that this measure mu is ergodic for the process seen from a second class particle. That's, well, that sort of has to be true for part two to be true, I think. And this proof, so starting from that coupling between product measure and the stationary measure, we get some fairly weak form of this convergence in part two. So we get that this sort of averaged over time, if we average between time 0t, some long, and then as big T goes to infinity, we get that the average of phi s is converging to mu. But it seems quite hard to get, using just these particle system methods, get any further than that. So then this is where some of these arguments involving coalescence of geodesics come in. So Lingfu and Allan are sort of virtuosos of this kind of arguments involving coalescence of geodesics. And so if we want to compare the measure at time t and the measure at time t plus s, the idea is, well, we can think of, now going back to the LPP picture, we think of a geodesic starting at level 0 and starting at level s, or maybe actually we'll start at 0 and start at minus s, and they're both going to go up to level t. So we have two geodesics which are slightly different lengths. They start slightly far away from each other, but then what's going to happen quite quickly is they're going to coalesce. So with high probability, two geodesics started near each other are going to coalesce quite quickly. And that's telling us that the difference between the distribution we see at time t and the distribution we see at time t plus s can't be too big. So that needs some really quite heavy machinery of the geometry of these last partial percolation geodesics. And that's very much Allan and Lingfu's side of this. I was very much more coming into this from the particle system side. But that's the main idea. So that ends up giving us the result we need for these semi-infinite geodesics. And then, as I was saying before, you need, again, some pretty heavy machinery for covering long finite geodesics by portions of semi-infinite geodesics, and you can get to these statements about the finite geodesics that I started with. Okay, but I think I'm running out of time. What I would love to have shown you is this nice combinatorial construction of the stationary distribution seen from a second-class particle. But yes, Pablo or I can show you that another time.
Okay, thank you very much, James. Let's unmute ourselves, please, and then applause. Yeah. And is there any question? So I have a question then. James, so with this argument, you get essentially the invariant measure as seen from a second-class particle, right?
Yeah.
But this is, in some sense, is a static picture, right? Because you see it at a given moment. And the thing for the last passage percolation looks like more dynamic because you are looking at the space-time picture.
Yeah.
How do you go from one to the other?
So essentially what you want to do is to look at the process seen from a second-class particle at the time of a typical jump. So essentially what you're doing is taking that stationary distribution and conditioning on a jump just having happened. So in other words, what you want to do is say, okay, I'm going to condition on a hole and a particle having just exchanged places at the origin. Well, rather the second-class particle having just exchanged places with either a hole or a particle. And you're saying, if I condition on that happening at time zero, let's say, what else has happened around time zero? So in the future, in the next thing that happens, in particular, so very specific question you could ask is how long until the next jump of the second-class particle? Mm-hmm. So if you ask how long until the next jump, that's just directly answering a question of what is the next weight on the geodesic. But you could also just ask more generally, given that happens at time zero, what are the events that have happened between time minus 10 and plus 10? And that tells you about, the values of G in a certain radius around the point that you're looking at. Mm-hmm. So yeah, I guess that's the idea that events that happen to nearby particles around the same time are telling you information about weights that are nearby.
So you are having a local space-time convergence for the TASEP.
Yeah. Absolutely. And I don't know how easy it is to calculate other nice things. In principle, these things, a lot of the extra things could be calculated, but yeah, so far we just did the easy.
Okay. So something that I understand well was that expression, that the limit that you got for the x squared and x e to the minus x. You said something that the weight of the geodesics, but I didn't understand what at the beginning. One of the corollaries of the theorem.
Let me go back. Yeah. So where we had this.
That thing. What do you mean here with that typical weight?
Well, it literally just means that supposing okay, let me take the weight that's halfway along the geodesic. Okay, so I take a big geodesic from 0, 0 to n, and I'd look at the weight that's halfway along. The distribution of that weight converges to distribution with that density function.
Okay.
Equally, if I just, if I sample, so you can do this is, when I came up with that formula, I wanted to check that it was true. And so you could just sample a long geodesic and get your computer to output the sample of all the weight, to sample all the weights along the geodesic and look at how their distribution function looks like, and it fits with that. So
okay, now I understand. Yes, but then now I ask if you have an interpretation of that distribution.
You can write it as a sort of mixture of sums of exponentials. So there's some, it's like some gamma functions. You have to sort of ask, okay, you've just seen a jump, and now you have to say, how long is it till the second-class particle next gets next to a thing it can jump with? and then how long does it take to, so I mean, the kind of calculation you need to do, let's say you've got your second class particle here, and let's say it's just exchanged places with a hole to its left. So then when's it going to jump again? Well, it has to either jump with a hole to its right or with a particle to its left. So you have to think, okay, how long is it going to take for this particle to arrive here? And then how long is it going to take for them to exchange? Or in the other direction, how long is it going to take for there to be a hole here? And then these two can exchange. So it's like you've got two competing things and you need to know which one happens first. And you get that kind of this distance here between the second class particle and the next particle is like a gamma distribution. No, sorry, it's a sum of two. No, I'm getting this wrong. That's like the sum of two geometrics, and the distance to the nearest hole on the right is another sum of two geometrics. And so you have some kind of, you get sort of sums of random numbers of exponentials until the next jump can happen. So it's not too, the calculation's not too difficult. I made it sound a little bit harder than it is there, but yeah, you're just sort of.
Okay, I understand. Okay.
And this, you can get this from this kind of queuing construction of the invariant measure.
Okay, thank you.
I have a more elementary question, James. So I understand that 1/2 plays a role because the second class particle won't have a drift, but so what's the importance in the proof? I mean, of this density.
Right. Sorry. So I absolutely should have said this. There's nothing really special about density 1/2. So except that the density of your TASEP corresponds to the direction of your geodesic. So instead, if you take density rho, that will give you a different direction for your geodesic. So if you want to know what the distribution looks like along a geodesic that goes in direction sort of 1, 2 or something, you'll need a different value of rho. You'll need a different density for your TASEP, and that will give you a different formula, which I haven't written down, for this density function. So for every direction of the geodesic, there's a different function you get here. So yeah, in the paper, we write everything with a rho in it the whole way through, but the notation gets just very cluttered up. And so I just decided to take rho equals 1/2 throughout here. But yeah, absolutely. There's no reason you have to take rho equals 1/2. There's no reason you have to take direction sort of 45 degrees.
Okay, thanks.
Is there any other question? Okay, if not, James, thank you very much. Let's clap. And so my role as host is finished now. So thank you, James. We will talk in another opportunity.
Yeah, well, thank you very much for having me.
Yeah, thank you, James.
Thanks, Claudio. Nice to see you.
Yeah, nice to see you too. Bye-bye.